In 2022, the James Webb Space Telescope turned its infrared eye toward the outermost reaches of our solar system, the frozen graveyard beyond Neptune, where the building blocks of the planets were left behind 4.5 billion years ago. The program was called DiSCo-TNOs. It was designed to catalog the surface chemistry of 54 objects orbiting in the dark at the edge of everything we know. Noemi Pinilla Alonso, the principal investigator and a researcher at the Institute for Advanced Study and the University of Central Florida, expected confirmation. The models were clear. These objects should be ancient, chemically simple, and consistent with a well-understood history of solar system formation. They were not. Pinilla Alonso said after the results came back that what excited her the most was realizing these differences were linked to the behavior of methanol, a key ingredient that had long been elusive on trans-Neptunian objects from Earth-based observations. Methanol turned out to be a defining clue. Methanol is not background chemistry, it is a precursor molecule, one of the raw materials from which amino acids and sugars assemble in the presence of the right conditions. It appears in the cold molecular clouds that exist between stars, before those clouds collapse to form new suns. Finding it preserved on the surface of objects in our own solar system, in concentrations that vary in patterns no formation model predicted, meant the history of these objects was more complicated than anyone had written down. Jonathan Lunine, a Webb interdisciplinary scientist and astronomer at Cornell University, had described the Kuiper belt before launch as objects in the graveyard of solar system formation. The data that came back made that phrase feel like something else entirely. What James Webb found in the solar system's graveyard was not what the standard model placed there. What it implies about what else is hiding in the dark beyond it is something that the physicists who have spent the last decade studying this region have not said out loud, at least not in public. The Kuiper belt was discovered in the 1990s, confirmed decades after Jared Kuiper predicted its existence in the 1950s, and in one of science's great ironies, Kuiper himself predicted the region would be nearly empty by now, swept clean by Neptune's gravity over billions of years. He was wrong. The objects are still there, orbiting in a flattened ring stretching from roughly 30 astronomical units from the Sun to what was, for 3 decades, considered the outer boundary at 50 astronomical units. 1 astronomical unit is the distance between Earth and the Sun, approximately 93 million miles. At 50 astronomical units, light from the Sun takes almost 7 hours to arrive. The objects out there approach absolute zero in temperature. They reflect almost no light. Finding them at all requires the largest telescopes on Earth pointed at specific patches of sky for extended periods, with no guarantee of seeing anything. The few things we did know about the Kuiper belt suggested a region of well-sorted, predictable debris, leftover planetary material, frozen and chemically unchanged since the early solar system. The standard model of solar system formation predicted this with confidence. Neptune's outward migration during the solar system's first 100 million years swept these objects into their current orbits, and the structure was supposed to be stable and thoroughly understood. Webb's near-infrared spectrograph covers wavelengths from 0.7 to 5.3 microns, precisely. The range where the molecular signatures of water ice, carbon dioxide, carbon monoxide, and complex organics show their strongest spectral fingerprints. When Pinilla Alonso's team examined the data from the 54 objects they had targeted, they found 3 entirely distinct compositional groups. Not 2, not a gradient. 3 categories that do not blend into each other the way any existing model had predicted. One group showed water ice as its dominant surface feature. A second showed concentrated carbon dioxide and carbon monoxide. The third showed methanol and complex organic molecules, including precursors to the chemistry of life. The standard model does not produce 3 groups. The belt has been frozen since before Earth existed. The models that describe it are less than 30 years old. These objects formed in the same general region, under the same general conditions, at roughly the same time. They should not have arrived at such different chemistry. The discovery team published the taxonomy in the Astrophysical Journal Letters in March 2025. The official language in the paper is precise and cautious. The implication: underneath the precision is not. The DiSCo-TNOs results were the first anomaly to come in. They were not the last. In February 2024, a paper appeared in the Astrophysical Journal Letters from NASA's New Horizons spacecraft, the mission that flew past Pluto in July 2015 and has been traveling outward through the Kuiper belt ever since, sending data home at the speed of light from distances that grow by roughly 1 million miles every few days. At nearly 60 astronomical units from the Sun, more than twice the distance to Pluto, New Horizons was still carrying a functioning dust counter, a simple instrument designed to detect the microscopic particles shed by collisions between larger Kuiper belt objects. The instrument was built to measure dust. The dust counter should have been reading near zero. Standard models predicted that the density of Kuiper belt objects, and therefore the dust they produce, would begin declining around 45 astronomical units. By 60 astronomical units, the belt was supposed to be empty. Alex Donor, a graduate student at the University of Colorado Boulder and the lead author of the paper, described what the instrument was actually registering: dust levels substantially higher than any model predicted. The outer edge of the known Kuiper belt was thought to be at 50 astronomical units. The New Horizons data suggested it extended to 80 astronomical units or farther. New Horizons chief scientist Alan Stern, speaking on April 4, 2024, was direct about what the mission had found. He said the evidence pointed to a second Kuiper belt, not an extension. A second one. The Subaru Telescope's Hyper-Suprime Cam confirmed the picture from an independent angle. In 30 nights of observation along New Horizons' flight path, the Japanese instrument found over 240 outer solar system objects. Most of them fell in the expected range. Then there was a gap. At 50 to 70 astronomical units, almost nothing, and then, at 70 to 90 astronomical units, 11 new objects clustered together, a distinct population in a region where no formation model had ever placed anything. Between 50 and 70 astronomical units is a span of 2 billion miles, roughly the combined distance from the Sun to Uranus and Neptune. Across that entire corridor, the Subaru survey found almost nothing. That gap is in the data. The cluster on the far side is also in the data. The models explain neither. Then came 2017 OF-201. Sihao Cheng, a researcher at the Institute for Advanced Study in Princeton, discovered the object on May 21, 2025, by applying a computational algorithm across archival telescope images from 2 separate observatories, the Victor M. Blanco Telescope in Chile and the Canada-France-Hawaii Telescope. He found the same object in 19 separate exposures taken across 7 years. It is approximately 700 kilometers in diameter, large enough, under planetary science criteria, to qualify as a dwarf planet. Its orbit extends from 45 astronomical units at its closest point to the Sun to over 1,600 astronomical units at its most distant. That farthest point places it near the inner edge of the Oort cloud, a region so remote that the Sun appears as just a bright star, indistinguishable from thousands of others. This object takes 25,000 years to complete a single orbit. When it last passed close enough to Earth to be detectable, the most sophisticated tools humans possessed were made of stone. Cheng addressed the implication directly. This object spends 1% of its orbital time close enough to Earth to be visible with current telescopes. One detection implies roughly 100 more objects of similar size and orbit that are, right now, too far away to see. The outer solar system is not the empty, well-understood boundary it appeared to be. And the things orbiting inside it are pointing to something that the people who study this region have not yet been permitted to name in formal settings. There is a separate problem that has been sitting in the scientific literature since 2016. In January 2016, Konstantin Batygin, an assistant professor of planetary science at the California Institute of Technology, and Michael E. Brown, the Richard and Barbara Rosenberg Professor of Planetary Astronomy at the same institution, the man who catalogued enough dwarf planets to force Pluto's demotion from the planetary lineup, published a paper in the Astronomical Journal. They had been analyzing the orbits of extreme trans-Neptunian objects, the most distant Kuiper belt bodies, with orbits so large they never crossed the paths of any known planet. After billions of years of gravitational interaction, these objects should have randomly distributed orbital orientations. They do not. The orbits cluster. The perihelion points, the points on each orbit closest to the Sun, align in the same direction across multiple independent objects. The orbital poles tilt the same way. In their 2019 analysis, Brown and Batygin calculated the probability that this alignment happened by chance. The answer was 0.2%. That is one chance in 500. That probability does not dissolve when observational bias is corrected for. It has been reproduced with different datasets, different correction methods, and different statistical frameworks. Brown's conclusion, stated publicly, was unambiguous. He said it is really difficult to explain the solar system without Planet 9. Batygin, asked about his personal confidence that something is there, did not reach for caution. He said 99.9%. The official language in NASA press releases, institutional briefings, and peer-reviewed abstracts has not changed in 9 years. The orbital clustering anomaly is described as exactly that, an anomaly. The planet remains hypothetical. The evidence remains indirect. That hedged language is not an accident. At a Planetary Society event with a microphone in front of him, Mike Brown set a public deadline for what is now an active telescopic search. He said, "Call us August 1st, 2026, and we'll tell you the answer." That answer is expected from the Vera C. Rubin Observatory, a new telescope on Cerro Pachon in Chile that achieved first light on June 23, 2025, and is currently conducting the Legacy Survey of Space and Time, scanning the entire visible southern hemisphere sky every few nights with a 3.2 gigapixel camera, the largest ever built for an astronomical instrument. Simulations give Rubin a 70 to 80% chance of detecting Planet 9 directly if it is a reflective body within its first few years of operation. The deadline is real. The silence, in the meantime, is institutional. If Planet 9 exists as a planet, the working model describes it as a super-Earth or mini-Neptune, 4 to 7 times Earth's mass, orbiting at roughly 290 astronomical units in an elongated path that takes somewhere between 5,000 and 10,000 years to complete. A 2025 study by Amir Siraj, Christopher Chiba, and Scott Tremaine used 51 extreme trans-Neptunian objects in 300 separate simulations to refine the orbital prediction. They give a semi-major axis of 290 plus or minus 30 astronomical units, an eccentricity of 0.29, and an inclination of roughly 6 degrees. At that distance, driving from here to its estimated position at the speed of a commercial aircraft would take longer than the entire history of complex life on Earth. In September 2019, a paper appeared in Physical Review Letters, the flagship peer-reviewed journal of the American Physical Society, that put a different question on the table. Jakob Scholz, a postdoctoral fellow at the Institute for Particle Physics Phenomenology at Durham University, and James Unwin, a theoretical particle physicist at the University of Illinois at Chicago, examined both the trans-Neptunian orbital anomalies and a second, unrelated dataset, an excess of unexplained microlensing events from a 5-year optical survey called OGLE. Both anomalies fit the same mass window. Both could be explained simultaneously by a single object, not a planet, but a primordial black hole. Primordial black holes are not the collapsed remnants of dead stars. They formed in the first fractions of a second after the Big Bang, when density fluctuations in the early universe created pockets of matter so compressed that space-time itself closed around them. At 5 Earth masses, such an object would be roughly the size of a bowling ball. Scholz and Unwin calculated that the probability of the solar system capturing such an object during its formation is comparable comparable to the probability of capturing a rogue, free-floating planet, which is already the leading hypothesis for Planet 9's origin. The optical telescopes conducting the most sophisticated search for Planet 9 cannot find a primordial black hole. It reflects no light. The Vera C. Rubin Observatory will tell us whether something is out there at 290 to 500 astronomical units. Batygin and Brown built their public deadline around that instrument's capabilities. Mike Brown has said that if Rubin finds something moving at that distance, it will almost certainly be Planet 9. He has also said that if Rubin finds nothing after a few years of operation, the hypothesis is very likely wrong. Sean Raymond, a researcher at the Bordeaux Astrophysics Laboratory in France, has been blunt about what a non-detection would mean for the theory. He called it pretty much dead. That is the telescope verdict. But Schultz and Unwin's paper carries no expiration. A non-detection from Rubin eliminates the planet. It does not eliminate the bowling ball. Noemi Pinilla Alonso's DiSCo-TNOs data revealed chemistry in the solar system's graveyard that no formation model predicted. Alex Dona's New Horizons dust counter found a belt that does not end where 5 decades of models said it should. Sihao Cheng's algorithm pulled a 700-kilometer world out of the dark, one visible for only 1% of its orbit, implying 100 more we cannot currently see. And Brown and Batygin have assigned a 0.2% probability to the idea that the outermost solar system is behaving normally. The telescopes are pointed. The deadline is set. The thing waiting out there at the edge of everything we thought we understood, whether it is an ice giant flung from the inner solar system by Jupiter, a planet captured from a passing star, or a relic of the Big Bang floating silently in the dark since before Earth formed, is the question that has not been permitted an answer yet. Are we ready to hear what August 2026 brings?